At dawn, the assembly hall smelled of oil and hot metal. The lamps hung low and orange, casting long shadows over rivet guns and benches, and the air tasted faintly of burnt varnish and coffee. Steel sang under impact, a quick metallic staccato that vibrated through steel toes and through the souls of the men and women who had stood for hours. Sweat sat on brows like a fine dust that glittered under the lamps. A fresh sheet of aluminum, barely warm from press forming, still hummed with the memory of pressure when a hand slid along its curve and felt the micro ridges left by the die. The sound of a test engine from the nearby run-up pit rolled through the open bay like distant thunder. The smell of leaded fuel crept up from the engine stands and settled like a warning. In the corner, a crate of new Merlin cylinder heads steamed as coolant evaporated in the chill of the pre-morning. "It will never hold at altitude," someone said across the benches, and the phrase landed like a verdict. Outside, on the other side of the channel, German radio stations had jokes. The design was mocked as a nice-looking plane that would never see the front. The claim from polite doubters and academies was simple and absolute. The Mustang, as fitted, would not endure the thermal and vibrational loads of long-range escort missions, and even with an improved engine, it would still be structurally fragile. They called it a lightweight toy. Inside the factory, the people who assembled those toys understood the stakes in a way that joking commentators could not. The planes were not curiosities. They were the difference between intact formations crossing for raids and bombers flying alone with gunners exhausted and empty of hope. Walter Archer, production engineer and the man who had reworked the jigs on the line, wiped grease from his hands with a stained rag and watched a fuselage skin aligned to the ribs. He had a thin scar along his knuckle from a press accident the month before, and when he touched the edge of the skin, he did so with an almost religious carefulness. "If these seams do not take the torque, the wing will sing itself apart," he said, voice low enough that only the immediate crew heard. His staff looked to him the way a crew looks to a watchman. They believed they could make something hold that the textbooks called unlikely. They did not tie hopes to slogans. They tied hopes to tolerances and to the smell of oil in the morning. The project carried human weights. Pilots flying their first long missions would clock out with eyes like open wounds if the fuel tanks cracked or never return at all. Families of workers lived a dozen blocks away in rows of houses with laundry on lines, and some spent pay to keep a mother alive. The stakes were counted not in abstracts, but in addresses and first names. Without a Mustang that could stay with heavy bombers to Berlin and beyond, bomber crews would be left to cross enemy airspace unsupported. That cost was not a metric on a sheet. It would be names on a list. If you believe that careful hands and stubborn engineering can rewrite a mockery into a threat, remember that while you watch. If you think they pushed too hard, think of the gunners on each bomber. What came next would decide who flew and who did not. But first it was necessary to understand why all prior designs had failed at range and altitude, and why a small change in engine and metallurgy might make the impossible routine. The strategic need was simple and exact. Allied daylight bombing doctrine depended on numbers and on the ability to keep formations intact for deep penetration. Early in the war, bombers flew with escorts that could not reach the targets and returned exhausted, if at all. Command staff had run the math and the geography again and again. To escort bomber streams to targets deep in the heart of enemy territory required an escort fighter with a combat radius of at least 1,200 miles when configured for economy crews. Few fighters had that range. The Mustang in one of its early forms had range but lacked high-altitude performance. The Army Air Forces had contingency plans that were brittle. The new priority order demanded planes that could arrive with bomber formations and remain until the bombs fell and the smoke cleared. Political pressure mounted in the war room and in the halls of industry. Air chiefs sent urgent memos. Reduce bomber loss ratios by half by the next quarter, read one terse directive. Factories were ordered to find ways to squeeze range out of fighters and to do it at scale. The problem was both aeronautical and industrial. An improved engine had to be matched to an airframe that would not crack under the new stresses. Supply chains had to stretch to provide new superchargers, different propellers, and thousands of extra rivets. When the designers suggested a radical swap of engine and a heavier supercharger, the first reaction from some military planners was thinly veiled skepticism. "Trade weight for speed and you endanger endurance," said a memorandum that wanted theory more than risk. On the floor of the plant, the need translated into sheets of tasks. Jigs had to be altered to accept new mounts. Test rigs were recalibrated. Engines would be trialed on gimbals and then in the test end of the runway. Every change was a negotiation between what physics permitted and what time allowed. The numbers mattered. A 20% gain in high-altitude power could mean the difference between staying with a bomber stream and being left behind. The factory schedules were mapped down to hours. A new engine meant new tooling, and the cost of mistakes would be human. When Captain Tom Reynolds, an operations planner, visited the line, he held a map and circled routes with a finger. "We need fighters that can be with the bombers from first light to late day," he said, and his finger tapped the paper with the steady impatience of command. Engineering-wise, the problem looked like a stack of trade-offs and a stubborn set of unknowns. The airframe had been designed around a different power plant. Swapping to a more powerful, heavier engine changed the center of gravity and altered vibrational modes. The cooling system had to be rethought for the new thermal profile. Early tests showed harmonic excitations in control surfaces that had never been anticipated. When the first prototype with the new engine taxied down the runway, an upper cowling panel vibrated loose and the pilot had to shut down. "The panel came off like leaves," the test pilot reported later in the log. A table of calculations had to be redrawn. In the engineering office, Walter convened a meeting that would become a model of stubborn civility. Around the drafting table, Margaret Cole, chief metallurgist, placed a small sample of treated aluminum alloy and tapped it with a metal punch so that the tool sang against the surface. Jean Morales, foreman of final assembly, had grease under her fingernails and a pencil behind her ear. Harold Briggs from logistics had a clipboard that had lived through 3 campaigns. Anna Petrov, quality inspector, had a quiet and precise voice. They argued out loud and sometimes with raised hands, and always with the sound of pressing tools near at hand. Dialogue between them became a working ritual, and in that meeting there were a dozen exchanges that moved the project forward. "How much more weight does the Merlin add compared to the Allison?" Walter asked, and his question cut to the geometry of balance. "It adds about 180 pounds at the nose," Margaret replied, as she laid down data, the paper rustling. "That shifts the center of gravity forward by nearly 2 inches, Jean said, and tapped a scale drawing. The sound of her pencil sharp against paper was like a metronome. "We can move avionics aft 3 inches and save the change," Anna suggested, and pushed a tablet across the table. "Moving the radios risks vibration coupling to the antenna mounts," Harold countered, and his finger tapped a logistic estimate. "We damp the mounts," Margaret said, and she drew a small sketch of a bushing, the line drawn by her hand steady. "The bushing material will need a higher temperature tolerance," Walter replied, and he looked at Margaret with the gravity of a man who had seen bushings fail in flight. "We can furnace treat a new alloy, but lead times are weeks," Jean murmured, and the faces in the room weighed the clock as if it were an engine. "Then stagger trials. If the first flight is to be meaningful, we must accept incremental fixes," Walter said. "Pilot will not accept a half." "Fixed plane," Anna replied with a crispness that suggested she flew too often in her mind. "If the pilot refuses, this will change everything," Harold said, and the tension in his voice mirrored the hum of a compressor outside. "We need a full test protocol with bailouts at each milestone," Margaret insisted, and wrote the first line on the pad. "Then we agree. Build to the protocol, and we fly when the data allows,"
Walter closed, and the room exhaled as rivet guns and presses resumed their argument with metal. Each exchange was short, utilitarian, and carried the smell of coffee and cutting oils. The cadence of the conversation matched the rhythm of the line, and when they left the table, they walked back into the heat of a hall that was both hopeful and worn. Early experiments were abrasive. A run on the vibration bench ended with a spar cracked at the junction where ribs met the main beam. The sound of that failure was sharp and dry like a bone breaking. A press operator lost a fingertip when a new jig seat failed to align, and for 2 days the line slowed as hands learned to compensate for the missing man. A fuel pump failed mid-test and drenched the floor in lubricant and fear. Sometimes the failures were almost comic in their persistence. Panels that had sat in the fixtures for hours would warp overnight when the humidity rose and then refuse to mate. Other times, failures were brutal and left people with scars and hospital stays. There were meetings that lasted until midnight. Faces around the table showed rings of fatigue, the skin pallid, and eyes red-rimmed from long hours. "If we keep chasing these anomalies, the schedule will slip," said a military liaison who tracked calendar weeks like currency. "If we push, we will make mistakes that cost lives," replied Margaret. The argument sharpened. The plant had to decide whether the imperative of time outweighed the demands of metallurgy. They did not agree easily. The next morning, a young fitter named Luke Hayes, who had been up all night repairing a misaligned fuselage, collapsed at his station from exhaustion. He recovered, but the incident left the group with a renewed sense of the human limits at play. The escalation of the problem led to inventive experiments. Margaret proposed a new treatment for the aluminium skin that would relieve residual stresses. She described a process that combined a brief high-temperature soak with rapid quench and a controlled natural aging that would change the microstructure in ways that improved fatigue life. The first trial panels left the annealing line with colorations like oil slicks, mottled and shifting, and when they were pressed into the jigs, they fit with a surprising compliance. The smell of heated aluminium and flux filled the lab. The panels returned to the vibration bench and survived cycles that had previously produced cracks. Another breakthrough came from an unexpected corner. Samir Khan,
a mechanician on the shop floor who had worked before the war in shipyards, suggested altering the exit geometry of the radiator ducting to generate a mild thrust at speed, thereby reducing net drag and assisting high-altitude performance. The suggestion was simple in line drawings and complex in simulation. Early computational runs showed a small net gain in cruise fuel economy and a drop in rear fuselage heating. The first physical trial included welding a modified duct and watching, with the sensitive smell of heated paint, as the system was run. Pressure gauges jittered, then settled. On the runway at the test end, the plane performed better than the models had predicted. It was a small gain, but in a problem that required trades, small gains accumulated. A short technical explanation must follow here in precise terms. The solution that combined a revised coolant duct shape and a higher altitude supercharger increased mass flow through the radiator core while reducing the pressure drop across the system. By shaping the lower lip of the duct as an ejector, the designers recovered a portion of the kinetic energy in the exhaust stream as axial thrust. The net result was a decrease in parasite drag at cruise and a moderate improvement in specific fuel consumption at altitude. The modification required reinforcement of adjacent skins to handle redistributed loads and a recalibrated fuel pump to maintain steady pressure at varying altitudes. The decisive test was organized on a cold, clear morning when thin frost clung to scaffolding and the runway exhaled vapor under the first engines. Pilots lined up, inspects signed their names in quick loops, and Walter stood with the test squad watching the first full configuration taxi and then roll. The compressor noise rose, the prop pitch bit the air, and then the aircraft swung into the sky. At 20,000 feet, the test pilot reported in a clipped voice over the radio. Climb rate holding, vibration acceptable, stability good, and roll. The telemetry returned smoother numbers than any prior run. Below, mechanics held their breath. and the sound of tools stopped in bays like a game of held music. There was an exchange between crew and pilot that stretched into a ritual of repeated confirmations and small jokes that allowed the tension to be managed. "You got the trim set on neutral?" Gene said over headset, almost laughing at the formality. "Trim neutral," the pilot answered. "Fuel feed correct?" Harold called. "Fuel feed stable," came the voice downlink. "Supercharger engaging at 11,000, the telemetry engineer announced with a small sense of triumph. "Roger," the pilot answered. "Watch that yaw when you add power," Margaret warned, and her voice was steady because she had spent nights in the lab. "I see you," the pilot said, and then, a private crack in tension, "I will bring it back in one piece." "We will keep it together here," Walter answered, and the meaning of that was more than maintenance. Each line in the exchange was short and chiseled by hours of practice and stress. The first successful sortie changed the tone of the factory and of the air war. When the plane landed and taxied back with smoke only from controlled exhaust, men who had not smiled for weeks let out short laughter. For the first time, the numbers matched the promise. The prototype had stayed with simulated bomber formations to beyond the required radius and had done so without structural issues. The radio chatter that night carried a new word among crews. Reliable was a modest claim, but it held enormous weight. The factory moved to ramp up. Lines retooled with new jigs and extra shift teams took on additional hours. The production geometry shifted from prototype carefulness to mass disciplined repetition. Subassemblies traveled on trolleys through stations where each operator had a narrow, expert set of tasks. Anna ran quality control with the quiet relentlessness of someone who had to sign off the lives of pilots on a sheet. She used gauges and go-no-go pins and a foot pedal that clacked in a rhythm. The numbers were impressive and granular. Production rose from a few dozen units a month to hundreds. A target of 500 airframes in a quarter became a new deadline, and the plant found creative ways to shave minutes off assembly times by pre-riveting bulkheads and reorganizing tool stations. Logistics were a mountain to climb. The engines were produced in a separate plant across a river, and transporting them required convoys and careful coordination. Each engine was tested on a stand for hours before being crated, and rails were loaded with protective liners. Fuel systems were calibrated at the assembly line and tested again on the ground and once more on the tarmac. The supply chains extended back to alloys and supercharger components, to propellers, and to the small things that mattered, like rivet counts and oxygen mask fittings. Shipping manifested to the front were planned by mathematicians who balanced capacity and urgency. In the field, the first squadrons received their Mustangs, and operational training squadrons worked to build tactics that took advantage of the plane's long range and high-altitude performance. When the Mustangs began to appear on escort missions, the strategic picture shifted. No longer were bomber streams left alone for the last leg. German fighter tactics that relied on intercepting bombers once their escorts had peeled back found the escorts persistent and angry. The Mustang could engage at altitudes and speeds that had been previously dominated by German interceptors. A tactic that had once relied on timing and surprise now ran into an adversary that could be present through the whole engagement. The effect on individual enemy pilots was stark and personal. German aces accustomed to dictating terms of engagement found themselves surprised by persistent escorts that could be there from takeoff to bomb run. Pilots whose reputations were built on striking at the vulnerable window when fighters peeled off found that the window had closed. The narrative of the ace was fragile and human. Friedrich Lang, a decorated pilot of the Luftwaffe, reported in his log that where he expected thin formations, he found thick, confident wings of Mustangs. "They would not break," he wrote, and the tone was not mockery but a kind of weary respect. Loss records from the months that followed showed an increased attrition among some of the most experienced units. The Mustang did not single-handedly win air superiority, but it changed tactical options and reduced the safe windows the enemy had depended upon. There were ethical debates alongside the tactical rejoicing. The frantic push to produce at scale meant longer shifts and a rise in injuries. Unions and civilian oversight bodies argued that safety standards had been relaxed and that some of the wartime urgency was used to justify excessive working hours. A meeting between the plant manager and a labor representative turned sharp when a worker spoke up about being sent back to a station with an injured wrist because the line could not wait. "We are saving lives at the front," the manager argued, and the worker replied, "We are risking hours on the bench." The answer was never simple. The war demanded output, and human limits demanded rest. The tension fed into evenings when men and women came home and tried to sleep against the background of factory sirens and news reports. 3 moments of acute tension reverberated through the project. The first was a high-altitude flutter event on a test flight where control surfaces vibrated and the pilot had to dump fuel and glide to a landing with the nose full of smoke. The minutes in the air where the instrument needle jerked and servo noises were uncertain lasted like an eternity for the crew and the engineers monitoring the feed. The second was a supply chain breakdown when a strike at a port stopped essential shipments of a hardening alloy, forcing the plant to cannibalize components and to build with altered heat treatments while a solution was found. The moral calculus of using makeshift parts versus stopping production was agonized over for days. The third was a friendly fire incident where a group of newly minted pilots misidentified a returning formation in poor visibility, and a mission ended with aircraft lost to miscommunication. Each incident added new procedures, more tests, and new training modules that rippled through the entire system. In technical detail, the metallurgy change that unlocked the fatigue problem had a clear description. The team adopted a controlled precipitation hardening route for the aluminium alloy used in the wingskins that increased yield strength while maintaining ductility. By adjusting solution temperature and quench rate, they promoted a fine dispersion of precipitates that impeded dislocation motion. The result was a material that tolerated cyclic tensile loading with delayed crack initiation and slower propagation. The treatment required exacting control of cooling rates and post-quench aging times so that dimensional stability was preserved during the riveting operations. Another technical note concerns the supercharger matching. The supercharger was selected to optimize power at cruise altitude rather than at sea level. By altering the gear ratio and impeller geometry, the designers improved mass flow at 20,000 feet and reduced thermal stress. The oil cooling system was redesigned to maintain stable viscosity across a wider temperature envelope and to avoid vapor lock on long climbs. These changes required additional baffles and seals and a minor reinforcement of mounting points to handle the increased torque. A third process explanation lies in the assembly technique that reduced stress concentrations at rib-to-skin junctions. The team adopted a lap riveting pattern with staggered pitch and introduced a thin adhesive layer to distribute loads across panels. The adhesive, a high-temperature-resistant phenolic composite, did not replace rivets but acted as a crack arrest system. The combination of mechanical and adhesive bonding reduced micro-fretting and increased the overall fatigue life of the wing. As deployment continued, the narratives of pilots and ground crews multiplied. Luke Hayes, the fitter who had collapsed months earlier, became known on the line for his meticulous alignment work and was later awarded a small commendation for saving an assembly that had a subtle misalignment. John Morales, who had kept the final assembly line together through arguments and shortages, later sat in a tent after a mission and watched a bomber formation return in a sky that had been dark at the mission peak. She had a photograph of her father from before the war pinned to a locker, and in that moment, with the smell of engine oil in the tent, she cried because the work had meaning that went beyond rivets. Day to day, the plane altered doctrine. Fighter groups extended patrols, and bomber crews gained confidence. The Luftwaffe adjusted tactics in response, and a few German units began to fly fewer deep interceptions and more conservative defense of key points. The attrition of experienced pilots affected morale. The phrase used in some German briefings moved from scorn to cautious acknowledgement. The Mustang did not root out all threats, but it made certain strategies untenable and forced adaptation. The post-action reports and numbers bore out the effect. Squadron loss ratios on deep raids declined measurably where Mustang escort was available. Bomber mission success rates climbed, and the ability to project power deep into the continent was sustained. At the same time, factory injury reports and production disruptions led to heated debates in Parliament and in civilian newspapers over the cost of pushing output. The moral ledger was complicated and full of names. 1 month after the first mass deployment, the factory had settled into a rhythm. Output was steady, and the first squadrons had developed tactics that used the Mustang to cover the bomber stream from the flank and to engage escorting enemy fighters with an emphasis on conserving fuel for the return leg. Pilots wrote home with new confidence, and letters circulated in the workers' dormitories. A memorial on the line was small and improvised, a board with names of those who had been lost in accidents, and a wreath of industry ribbon. The sense among the workforce was of cautious pride. 3 months later, the strategic charts looked different. Targets once deemed too risky had been scheduled again under the cover of continuous escort. Losses for bomber formations in theaters where Mustangs were present showed a notable decline against the prior quarter. In the factory, improvements on tooling had reduced assembly time by 12%, and a new quality checklist instituted by Anna Petrov had caught subtle defects that might have led to in-service failures. The debates in public about labor standards had cooled into reforms. The company instituted rotated shifts and better rest provisions, which slightly increased per-unit cost but stabilized the workforce. The morale in the plant was higher, and the photograph of Walter and Margaret taken in the heat of expansion showed fatigue, but more often a slight, guarded optimism. 6 months in, the change in doctrine had taken firmer hold. The Mustang had transitioned from a mocked newcomer to a pillar of sustained escort strategy. Pilots famous in early war reports as uncatchable had their kill rates drop. The career arcs of some aces changed when continuous escort made opportunistic attacks riskier. In historical terms, the plane contributed to a shift in air superiority dynamics and opened windows of opportunity for strategic bombing that would have been unlikely without it. The engineering advances in metallurgy and in cooling systems migrated into civilian applications after the conflict. Factories that had learned to run at wartime tempos retooled again, and some of the practices of fast assembly informed post-war production in transport and industrial machines. In personal terms, the legacy was mixed. There were reunions of crews, and there were small plaques in towns naming the men and women who had worked through nights. There were also stories of those whose lives had been shortened or scarred by the rush that the war demanded. Lessons were learned about the balance between urgency and safety, and about the imperative of recognizing human cost as part of any technical gain. The final image is both simple and complex. In a hangar, years later, a retired mechanic runs a cloth over an old fuselage panel and feels the smoothness of a treated alloy that had once been the focus of sleepless nights. The metal keeps the memory of those hands and the practice that bent it into shape. The Mustang line changed not just the map of aerial combat, but the craft of manufacturing. The machine that the enemies had mocked became a machine that many trusted to bring their sons home. That trust was paid for in endurance and in sacrifice, and it becomes our question now. How do we weigh the costs of speed against the value of lives, and how do we remember those who held both the rivet gun and the front line? If stories of hidden hands and stubborn engineering move you, please subscribe for more detailed reconstructions of the inventions and people who shaped history. And tell us in the comments whose hands in your town deserve to be remembered.